So in this question, we have a bullet colliding with a stationary block, and we are asked the maximum height that this block will rise above its initial position. And it turns out we have to solve for that by breaking the problem into two separate phases. Let's take a look at phase one of the problem. So here is a representation of a collision between the bullet and the block. We have called the bullet object 1 and therefore have labeled it M1, and the block is object 2 and we've labeled that as M2. We have the initial velocities stated, so the bullet was going 1,000 meters per second, and the block is initially stationary, so its initial velocity, of course, is 0 meters per second. Also, notice we've converted the mass of the bullet into kilograms by multiplying the grams by 10 to the minus 3. So we have this initial phase of the problem where the bullet is launched towards it, and then what happens is the bullet passes through the block, and that's going to send the block flying upward with some initial velocity, which we'll be using in the second phase of the problem. So basically what we're going to do is take the initial and final here, and we're going to apply conservation of linear momentum. So let's take a look at what that would mean. It would basically mean that the initial momentum of object 1 plus the initial momentum of object 2 would have to equal the final momentum of object 1 plus the final momentum of object 2. Now, let's expand these momentum expressions. We know that momentum is mass times velocity. So for the bullet, we would say m1 times v1 initial, and then for the block, we would have m2 times v2 initial. And on the other side, basically the same thing except final parameters. So m1 v1 plus m2 v2. Now it's relatively easy because we have listed out all of the known values along with our unknown. So let's go ahead and plug in all of the given data. So all of the data has been plugged in. Notice that the value right here is going to go to 0 because we're multiplying 5 times 0. We can simplify the right-hand side a little bit here. We can multiply these values out, and we end up with 4 kilogram times meters per second. Similarly, we can simplify over here. This turns out to equal 10 kilogram times meters per second, and then we have this plus 5 kilograms times v2. Of course, our next move here is to subtract the 4 kilogram meters per second from both sides. This goes to 0 here, and now we have 6 kilogram times meters per second. This is equal to the 5 kilograms multiplied by v2, and then finally we will divide both sides by 5 kilograms. So these cross off. We are left with 1.2 meters per second. This is equal to v2. Let's recall what that actually represented. This was the final velocity of the block after the bullet had passed through it. So now you can imagine this block is launching upward with an initial velocity of now 1.2 meters per second. Now, we're calling this an initial velocity because now we're moving into phase 2 of the problem. In phase 2, we're going to conserve mechanical energy. So let's take a look at that phase. So here we are after the collision. Again, the block is launched with some initial upward velocity of 1.2 meters per second, and then it's going to rise to some maximum height whose value we are trying to figure out. Now, notice when the block reaches its maximum height, it momentarily comes to rest. So its final velocity is going to equal 0. So now you want to ask yourself, what sort of energy is present in the initial picture? What sort of energy is present in the final picture? Now, hopefully we understand that initially, all that we have is kinetic energy. The block has not lifted off of the surface yet. It is moving, but because it's only moving and not yet lifted off the surface, it possesses only kinetic energy. On the other hand, once the block reaches its maximum height, it's no longer moving, but it is above the surface of the ground, so it's going to have some final gravitational potential energy. Now, we can expand each of these expressions. We have 1/2 multiplied by the mass of the block multiplied by its initial velocity squared, and then on the other side, we have the mass of the block multiplied by g multiplied by that maximum height. Now, you'll notice that m2 appears on both sides of the equation, so it would actually divide out. That is convenient. We can simplify the equation. And then finally, we could solve this for h, which is what we're trying to find, so we'll divide both sides by g to solve for h. And then finally, we will plug in that initial velocity of 1.2 meters per second. Don't forget to square it, and then divide that by the gravitational constant, 9.8 meters per second squared. And when you plug this all in and simplify it, you will find that the maximum height to which the block rises is about 0.073. And that will work out to meters. This is the correct answer to the question. So, two phases to the problem. Phase one, recall, was to conserve momentum. That allowed us to calculate that initial launch velocity of the block that we then used in phase two, which is a conservation of mechanical energy.